All right, so how are we going to rearrange this equation in order to discover the relationship between r and e instead of the relationship between r and log e? How do you make e the subject? What should I do here? Right. I need to get that e by itself, but e is inside of a logarithm. So I just need to do the opposite, the inverse function, of the function that's being applied to my e. I just need to use an exponential, and the base of that exponential should be the same as the base that's implied by our common logarithm over here, a base of 10. So I'm just going to make both sides of this equation the exponent in an exponential expression whose base is 10. That's a long-winded way of saying I'm just going to do this. 10 raised to the left-hand side power must be equal to 10 raised to the right-hand side power. And the point of all that was what happens on the left-hand side. When you raise 10 to whichever power 10 must be raised to in order to get e, the result is e. Unpack that sentence a few times. Point is, base 10 logarithm and a exponential power with a base of 10 are inverse operations. So they kill one another, and we get just plain e on the left-hand side. And then we get some kind of nasty-looking thing on the right-hand side. We get 10 raised to the power 3/2 r plus the log of 2 minus 9/2. Log 2 minus 9/2. And I suppose we could leave it like this if we wanted to. But let's just dust off some of your J-problem skills from yesterday and see if there's a way to simplify the expression that we have on the right-hand side. First of all, I've got addition happening up here in my exponent. How can I make that look different? Instead of the arithmetic being in the exponent, I want that arithmetic to be downstairs in the base. So what does it turn into when you move addition in the exponent downstairs? When you're adding exponents, what are you doing to their powers? You're multiplying the powers. So I'm going to turn that addition upstairs into multiplication downstairs and give each one of those exponents that were being added, I'm going to give it its own base. So that's 10 to the power log 2. And then I suppose we also had this minus sign going on up in the exponent. And a minus up in the exponent turns into what in the base? If addition turns into multiplication, then subtraction turns into division. And so I end up getting, if we put the 9/2 in its own base, we get divided by 10 to the power 9/2. All right, now the last thing I'm going to do is, so we're going to have 10 to the power 3/2 r. Let's take this middle factor, 10 raised to the power log 2. What is 10 raised to the power log 2 equal to? 2. The 10 and the base 10 log, once again, canceling one another out. And so I'm going to get times 2 divided by 10 to the 9/2. So maybe I'll just write that like this. 2 divided by 10 to the 9/2. And that's just some number, some constant, right? We could find a decimal approximation for that constant if we wanted to, but I think in the interest of time, we'll just leave this relationship as it is. And there is a simplified relationship between the energy released by a seismic event E and its measurement on the Richter scale R. And notice where that slope ended up in our final equation. It ended up here as a coefficient of R in the exponent of a power that has a base 10. But if you were to be given this equation by an enterprising earth science professor, let's say, and asked to interpret what some of these parameters mean, you would probably want to do this process in reverse. Linearize the equation, take it back into this form, And from that form, you can then discover the interpretation that we had from before.